Okay, so I'm going to go over some oxidation stuff for you guys, some general rules, and some good foundational stuff that you're going to need. So, first and foremost, we've got our rules here. I'll move the camera here in a second. Hopefully, it gets everything. But you always have to come back to these rules right here. You've always got to come back as you're trying to assign oxidation numbers. So, before we even get to that, just quickly, the point of this is these are redox reactions. So these are reactions where electrons are moving one substance to another. So we need to figure out where they are coming from, where they are going. And so if it's oxidized, it's loss of electrons. If it's being reduced, the substance then gains the electrons. So we have to assign these oxidation numbers to each element within each compound within each equation or reaction. So that's the point of this. So we'll start here. I'll try to get to all of these and try to give you guys a little bit of an example. I'll go through a couple examples that are on the PowerPoint that's in Schoology. I will go over the worksheet that we started today, a couple of the problems there, and then, if you guys have any questions beyond that, you can let me know. So first thing we have here is free unbonded elements have an oxidation number of 0. So some examples of that would be carbon. Okay, just carbon by itself. If you see carbon by itself in an equation, then you know that that is going to have an oxidation that equals 0. Or as we will start to label when we get into the reactions and start labeling the equations themselves, we'll put that right above the actual element. The main thing that students get confused on with this is, okay, free unbonded, does that mean just by itself? No, you can have multiple. So if I take a sulfur and I throw 8 sulfurs on there, so I have 8 atoms of sulfur now, it is still 0. So don't be confused with the subscript telling you how many atoms are present there. It doesn't matter. It's still going to have an oxidation state of 0. So what you're really looking for, is it by itself? Is it unbonded? So if I had sulfur here and then I added oxygen onto the sulfur, then rule 1 no longer applies. So if it's by itself, doesn't matter how many, if it's by itself, you have an oxidation number of 0. So that's rule number 1. So free unbonded elements equals 0. All right. So monatomic, same as its charge. So mono, single, atomic, so we have 1 atom, but it has a charge. So in this case, we have, let's just take magnesium and we go 2 plus. That was one of the examples in the PowerPoint there. That's going to have an oxidation number of +2. So I'm also differentiating here when I'm writing these numbers. If I put the charge off to the side, I'm putting the charge second number first, and then in the oxidation number, I'm putting the plus, and then the charge, and then the number second. So that would be that. So whatever you have now, when that doesn't apply is, again, if I put another element onto there. So if now I take magnesium and I add an oxygen to it, well, now, and I'll just throw up a charge there, even though that probably wouldn't have a charge on it. I'm just putting it out there for an example. Now it is no longer a monatomic ion. It is now poly. So just to be correct here, let's put an actual poly up there. All right. So now we have carbonate up there. Well, we have multiple elements bonded, and we have a charge. So no longer is it monatomic, it is a polyatomic ion. So for number 2, monatomic. So if you see an element by itself, then we will have the, let me just get another one here. It doesn't matter, I'll throw up Na plus. All right, so by itself with a charge, it will equal its charge. So that would be a +1 on there. All right, so that's rule number 2. Okay, now we move on to rule number 3. Super important because we are going to see a lot of alkali metals and alkaline earth metals within our compounds as we're assigning our oxidation numbers. So alkali metals, group 1 +1. Okay, so a general rule, what we want to do as we're trying to assign these numbers is we want to address the elements that have rules first. We want to address these elements that are alkali metals, alkaline earth metals, oxygen, hydrogen, fluorine. We're going to get to those, but we want to address what we can apply a rule to first. Assign that number there first, then we can deal with the other elements that are more variable in their oxidation numbers. So alkaline metals, +1. Alkaline earth metals, +2. All right, oxygen, hydrogen, fluorine. Okay, so I say the two beasts of this are oxygen and hydrogen. They're constantly there. They're constantly in these equations, in these compounds. You're going to constantly see them. So it's super important that you get used to these numbers. So we have, let's go down a little bit here. We have oxygen is going to be -2. So most of the time, oxygen is -2, except when it's in a peroxide. So when we have O2 to negative, all right, in that case right there, then oxygen would have a oxidation number of -1. Okay, each one of those oxygens would be -1 to give you that. So the second one would be H2O2. So if you see H2O2, then it's the same thing. Each one of these oxygens would be a -1. But that is definitely the smaller portion of oxidation numbers when we're dealing with oxygen. Most of the time, it is going to be your 2 negative for oxygen. Okay. All right. Hydrogen, also same kind of concept here, guys. Same kind of concept. Most of the time, it's going to be +1. Most of the time, unless it's bonded just with a metal. All right. The main thing that people deal with that and struggle with this concept is what do you mean a metal? Because hydrogen is constantly bonded with metals. Well, what I mean is if it's just the metal and just hydrogen, that's it. So, for example, if I take hydrogen and I bond it to iron, let's say, all right, and then I say, okay, well, I've got hydrogen here and I've got iron right here, but then I'm going to throw on an oxygen. Okay, well, these are two different scenarios that warrant two different oxidation charges. So in this case, all you have is hydrogen and all you have is iron right here together. When you have these two things, that's it, no other elements, then hydrogen now is going to take on that -1 oxidation number, and iron then will have the +1 if this is a neutral compound. All right, and we'll get into determining all that here soon enough. But for right now, that is the scenario where hydrogen is -1. That's it. So here it is not. It is not hydrogen or -1. It is now a +1 because I have another element involved here. Okay, so it's no longer just hydrogen and a metal. Now it's hydrogen, a metal, and oxygen. And I could take, chlorine or fluorine or whatever and put it right there. It doesn't matter. So this is what you need to look for: just hydrogen, just another metal, and then we have that right there, that -1, and you will see that some. So you need to be careful of it. Also, be aware. I mean, you know, sometimes things like calcium and beryllium that you don't really think, or lithium, you don't really think of. Well, lithium's kind of, you would think of a metal, but calcium would be a good example where you wouldn't think that calcium's a metal, but it is. So be careful that you assign hydrogen that -1. So that's a big one right there, and we've had multiple students struggle with that. So now, fluorine and aluminum, those are constants. So fluorine is going to have a -1 charge. Aluminum is going to have a +3 charge. You'll see both of those a fair amount. And so, as a general trend, and that's what kind of makes this thing difficult, is there's general trends. There's not absolutes that you want to see. You want to see these absolutes because it makes things easier. But general trends, you see a halogen, it's going to probably have that -1 oxidation charge, but it doesn't mean it 100% will. Ultimately, this is based on electronegativity, the greed for electrons. How greedy are you for electrons? And the greedier element is going to take them. And that is based on electronegativity. So Now let's get on to number 5 and 6, and these are the ones that have a process with it, and we'll do some examples with this. So number 5, neutral molecules have to add up to 0. So this is kind of like an equation that we're working with, and we have to make it true. And so when you see a compound that does not have a charge on it, then we are going to make it 0. We are going to have to add it up to 0. All right. So in that case, let's look at a couple examples here. So I'm going to go to let's go to the one. This is in slide. This is on slide number 8 in the PowerPoint. K2 CO. Okay, so just made this up a little bit. Just made this compound up. We have potassium right here. We have cobalt, and we have iodine. All right. So when we are working with this, I'm going to take this down for a second. When we're working with this, there's a process. And as you guys know, you know I'm big on the process. Stay with the process. Be consistent with your process. Do the same thing. All right. This consistency will lead to accuracy, which is what you want. So what we're going to do is, since there is no charge here, we're going to set this thing up and we are going to make it equal to 0. Okay, we have to make it equal to 0. So I'm going to rewrite this where each individual element will have its own space. So make sure that when you're bringing this down, you bring your subscripts as well, telling you how many atoms you have. So K2 plus your cobalt there plus your iodine right there. All right, so we are going to make that equal to 0. All right, so we're going to go a couple lines down because we want to keep track of everything. So I'm going to put equal to 0, because we're going to have a couple lines there. I'll put my plus signs in, set this whole thing up. All right, so from here, I am going to start assigning oxidation numbers, but the big thing here is where do you start and where do you go? So that's the main confusion. Where do you start? Where do you go? And it's important that you start at the right spot. I try to start on the right if I can, but ultimately we start with whatever we have a rule for, and then we work our way through it. So we do have a rule right now for potassium, because potassium is going to be an alkali metal. So that was one of our rules. That was rule number 3 there. Alkali metals are +1. So in that case, we're going to put a +1 right there as this oxidation charge. Now, the next step in this is going to be, there are 2 atoms of potassium. So we're going to multiply that by 2. We'll put that 2 right there in parentheses. So we're going to multiply those 2 things, and 2 times 1, of course, is going to be 2. So we have a 2 there, +2. All right. So you see these transition metals, and we see on the periodic table there are multiple oxidation numbers that it can have. So there's a variance there. All right. And I'm not saying that there isn't, halogens that can't vary too, but they're more constant. So in this case, iodine being a halogen and already having 7 valence electron and wanting the ocho, they want that 8, right? So it's going to grab that last one and have that -1 charge. That's what these halogens are going to do. So with that in mind, we know that, okay, well, iodine here is going to have a -1 charge. So I'm going to put a -1 right there. And since there's 3 of them right there, I'm going to multiply that by 3. All right. So now -1 times 3, of course, is -3. So now we're set up, right? We've got to make this true. This has got to be true. And for this to be true, then 0 equals 0. Nothing else is going to make sense unless this side is 0 as well to equal that 0 on my right side. That's the point. So right now we're at -3. If I take that +2 and I apply it to that -3 right there, then I'm still at -1. Okay, so I've got to bring it up to that 0. So that means my cobalt is going to be +1. That's going to be my value for that. All right. Now, don't be scared to assign what you need for that cobalt. That's what I like to call my buffer. So that's my buffer to get me where I need to be within this equation to make it true. So I've got 1 cobalt, so I'm just going to multiply that by 1. So 1 times 1 is going to give me 1. So 2 plus 1 is 3. This right here is going to equate to 3. And that's going to counter my -3 and make it 0. So ultimately now I have made that true. And let me just go back one more second to what I was saying about the cobalt. especially with transition metals, since they have multiple oxidation states. Metals like to give up electrons, so they do have these multiple states. So you can use these, okay? So also outside of the rules, as far as alkali metals being, the +1, and alkaline earth metals being +2, and my halogens being that -1, and oxygen and hydrogen that we went over, besides that, there's variance there. You don't just think, okay, cobalt is +1, so every single time it's going to be +1. That's not necessarily the case, but we can save those elements like transition metals for the end and use them how we need them to get to where we need to be to balance this side to zero if we're talking about a neutral compound. Okay, so we're almost done, but not quite. Be careful. Don't take what you have got right here and transfer it up to put as our oxidation numbers. We still have one step left. These oxidation numbers are on atomic level, like one atom, right? It's a singular type deal that we're describing here. So iodine on an atomic level, a singular level, is not -3, as we talked about. It's at -1. So just take your subscript here, how many you have, and just divide it by your final answer that we have here. So -3 divided by 3, of course, is your -1 there. You can divide that by 1. It's not going to change anything. +1 there. We have 2 here. We're dividing that, and that's also going to give us a +1 right there. So something to be cautious of and be aware of as well that I've seen some students struggle with is, remember, we've balanced this down here. This is equating to 0, making this true. Don't get confused and think, oh, I just put my atomic numbers up here, and that's not equating to 0 here. This, because that's +2 minus 1. That's not going to be 0 anymore. We're not doing that up there. We're assigning each atom of that element an oxidation state, because eventually, when we get to the equations, we will figure out what's being reduced and what's being oxidized. And that's the point. That's the point that we're doing. So don't be confused by that up there. We're going 0 here to equate to 0, but up here we're just assigning them their numbers there. Okay, so that is for a neutral compound. So I'll do one more for you guys, and we'll go on to a poly, and I'll do a couple there, and then that'll wrap it up here. So based on what I just showed you, go ahead and try. Let's go. I'm going to pull up that worksheet, and I'm going to do this problem right here on the worksheet. It's on the worksheet. It's F. So this is Al, aluminum, and hydroxide right here. Okay. So go ahead and try to assign those oxidation numbers on there according to what I just went over, and see if you can't get that knocked out. So you can pause the video real quick and try to knock that out really fast. All right, so again, no charge, neutral. So I'm going to assign my numbers. Now, this is just upping it up one step, but you guys already know that when we have parentheses right here, we're distributing that in, that subscript 3, and it's saying we have 3 molecules of hydroxide. That's what that's telling us. So now I'm going to go ahead and give everybody their own space here. So aluminum plus my oxygen plus my hydrogen right there. No charge, so it's going to equate to 0. But now I need to distribute through. That's going to give me 3 oxygens. That's going to give me 3 hydrogens right there. And of course, that matters that we have the right number of atoms as we're trying to balance our sides with 0 and 0. Okay, so hydrogen, we have a rule for hydrogen. We have a rule for all 3, honestly. So this is actually quite simple. We have a rule for hydrogen being a +1 unless it's bonded to directly with a metal, and that's it. And that's not the case here. So we have, let's go ahead and put our plus signs in. And bring that 0 down. All right, so we have a 1 plus 1. We're going to multiply that by 3 because there's 3 atoms. That's going to give us 3. Oxygen is going to be -2, so -2. We're going to multiply that by 3 since there's 3 atoms of oxygen. That's going to give us -6. And so as we stand right now, -6 and +3, so we're still at -3. We got to get another 3 in there to get to 0. And lo and behold, there's our aluminum, which is going to have a 3 plus charge with 1 atom of that is going to give us 3. So that's going to equate to 3 plus 3. That positive is going to give +6. It's going to balance that -6 to give us 0 on this side, which of course will match that. Now we just have to divide to get our final oxidation numbers in here. So we have 3 atoms of hydrogen. We're going to divide by 3, which is going to give us +1. We will divide by 3 here, which will give us -2. And of course, we have 1 here, and that's not going to change anything. So that's going to be +3 on my aluminum. Okay. All right. Great. So I am almost running out of time. My planning period's almost over. I've got like 4 minutes. So I'm going to go over the polys really quick with you guys, which is the last rule that we got. You finish it? All right. And make sure to grab that sign on your way out if you don't mind, man. All right. So right here, my last rule down here at the bottom states in a poly oxidation must add up to the charge. So now for that, we're going to use a poly. So let's see. I'm going to go grab one off of the PowerPoint. Let's go with CA. Let's do this. CA2 NO4 2 negative. So we see that we have a poly with the charge right here. So 2 negative is going to be our charge. So same process, guys, same process, except we're going to set it to equal -2. That's it. That's the only difference here. So we'll go ahead and give everybody their space. So our calcium here plus nitrogen plus oxygen, O4, equals -2. So when I bring this down, I have to do the same thing, -2, -2. I go plus, plus, I go plus, plus right there. All right, we're set up. So go with the rules first. Go with what you have rules for, and then we'll use whatever's left over to help us out balance this thing out. So oxygen's right here. We have a rule for oxygen, and it's not in a peroxide, so we know it's -2. So -2, we're multiplying that by 4. -2 times 4, of course, is -8. All right. So we're skipping nitrogen. We don't have a rule for nitrogen. And it's a variant, so it can be multiple things. It can be positive or negative. So here we're going to come over to calcium because we have a rule for calcium. Calcium is an alkaline earth metal. So when we look at our alkaline earth metals in group 2, we know that that's going to be a +2 because rule number 3 says so. So we're going to go +2 there, multiply by 2 since there's 2 atoms there, and that's going to give us 4. All right. So where do we stand? We have -8, we're adding 4 to it, so we're at -4 right now. We need to get to -2, so all we need is 2 more. So that means that my nitrogen is going to be 2, and we only have 1 nitrogen, so that's going to be a 2 positive right there. So 6 positive added to a -8 is going to equate to a -2, and we now have made that equation true. We have made it true. So now we will do the last step, which is divide to get our oxidation numbers up top. We have 4 right there. We're going to go ahead and throw our 4 right there. So 8 divided by 4, of course, is our -2. That's by 1. It's not going to change anything. That's a +2. And right here by 2, that is going to give us a +2 right there. So there's our oxidation numbers right across the board. And as you can see, like I talked about earlier, that's +4 and a -2, which is a +2, which is not going to equate to what we were trying to do there. But that's okay. That's not what we're trying to handle. We're handling that down here. This is a product of what we're doing down there. All right. So really quick, I'll try to do one more poly for you guys. I'm going to be rushing because the bell's about to ring. But I'll try to get this through. Pause the video when I put this up. Let me see. Let me grab another one. All right. Let's do this. Let's go. This was also in the PowerPoint. So H2 N2O5, and that's a 2 negative. All right, there's the bell. So I'm going to pause it real quick, try to knock it out, and I'm going to run through this really fast for you before my next class comes in. So really quick, we have a poly, so it's going to be set to a -2 charge. So let me give me some space for my stuff. And 2 plus O5 is going to equate to -2. All right, so quickly bring this stuff down. -2, -2. All right, so that's going to be -2 because it's an oxygen. It's not just it's not in a peroxide. So -2 times my 5 is going to give me -10. Now we're skipping this. This is our filler, right? This is going to be our buffer. Come over to the hydrogen. We have a rule for that. Hydrogen's +1. It's not -1 because it's not just bonded to a metal. So +1, and we're going to multiply that by 2. So that is going to give me 2. So now in this case, we have -10 plus 2, we're at -8, and we have to get to -2, which is 6. Okay, 6. Now, you can't just put a 6 here because if you put a 6 and multiply by 2, that's going to be 12, and that's not going to work. So we have 2, so we have to split that. So what can you multiply by 2 to get 6? All right, and of course, that's going to be 3. So we put 3 right there, and we're going to multiply that by 2 to get 6. 6 plus 2 is 8. We're going to add that to the -10, which will give us -2. So last thing, we just got to divide. We're going to divide by 5. We're going to get a -2 right there. We are going to divide by 2. We're going to get a +3 right there. And we're going to divide by 2 to get a +1 right there. And we are done. All right, guys. I got to go. But if you have any additional questions on this stuff, let me know. Let me know if you need some more videos as we start getting into our actual redox reactions and putting these oxidation numbers on there so we know what's been reduced, what's gained the electrons, what's been oxidized, what's lost the electrons, and then do our half reactions for that, and then determine and state which is our oxidizing agent and our reducing agent, which we will be getting to over the next couple of days. So just stay in contact with me, guys, and let me know how you're feeling about this stuff.